Let's say we have a very simple circuit like this, where we have a 5-volt battery that sets up a potential difference across this circuit and a simple light bulb. If we now attach a voltmeter in parallel to the bulb, we get a reading of 5 volts. This means there is a drop of 5 volts across the ends of the bulb. Now, it doesn't have to be a bulb. It could be a motor or a heater or any other electrical device that causes a reduction in voltage. The potential difference created by the battery provides the energy needed to move charge through this device. So in this case, the charge is free electrons. And this potential difference between any 2 points in a circuit is a measure of the energy transferred or work done by each coulomb of charge. And we can write this as an equation. So we've got potential difference or voltage on the left-hand side is equal to the energy transferred or the work done on the device divided by a unit of charge. So now imagine we have 2 circuits with the same setup, but with a different voltage across the circuit, and therefore each of the bulbs. The current in both circuits is also the same at 1 amp. So how can we calculate the work done or the energy transferred to each of these bulbs here over a 10-second time period? So we know in circuit 1 that our voltage is 240 volts across the bulb here. We've set the current to 1 amp. And we're trying to measure the energy transferred to this bulb over 10 seconds. And we're also going to need to work out how much charge is going through these bulbs over the 10-second time period as well. Now, if you come this far studying electricity in your physics course, you would have learnt that the size of an electric current at any point in a circuit is given by the rate of flow of charge. So in other words, how many charged particles are moving through a cross-sectional area per unit time. And this gives you the current at this particular point in a circuit. And because we know the current for both our circuits and the time, we can isolate the charge here by rearranging this equation. So if we look back at our original equation, where the potential difference is equal to the energy transferred divided by the charge, we can now replace the charge in this equation by the current multiplied by time. So we come up with new equations for circuit 1 and circuit 2. Now, because we're interested in the work done or the energy transferred to each of these bulbs here, we can rearrange this equation to make the work done the subject of the formula. And because the current and the time is the same on both circuits, we can see that the work done or the energy transfer to each bulb is proportional to the voltage across it. So once we plug in all our values into both these equations here, we find out that the energy transfer over 10 seconds in circuit 1 is 2,400 joules, but in circuit 2 it's only 50 joules. So given this information, what bulb do you think will shine the brightest? The bulb in circuit 1 or the bulb in circuit 2? Well, more energy is being transferred to the bulb in circuit 1 than in circuit 2. So the bulb in circuit 1 will shine brighter. So if we try another question now, an electron in a particle accelerator is accelerated through a potential difference of 1 million volts. Calculate the energy in joules gained by this electron. And the charge of an electron is minus 1.6 times 10 to the minus 19 coulombs. So if we go back to our first equation again, where the potential difference is equal to the energy transferred divided by the charge, we're interested in how much energy has been transferred to this electron as it's accelerated through this potential difference. In other words, we're looking at the change in kinetic energy of this electron. Now, because the electron is gaining kinetic energy, we know that the change in kinetic energy, or the work done, is going to be positive. So in this case, we're going to take the absolute value of the charge of an electron so that we get a positive value. So when we rearrange this equation, the energy transferred to our electron is equal to the voltage multiplied by the charge of this electron. And we've increased this electron's kinetic energy by 1.6 times 10 to the minus 13 joules. So let's now talk about electrical power. In a previous lesson, we defined power as the rate of doing work or the rate of transferring energy, where the power is equal to the work done divided by time, and it has units of joules per second, or watts. For electric circuits, however, it would be more useful to express power in terms of voltage and electric current. To do this, we're going to use two additional equations to help us out. So the first equation is one involving current and charge. So the current is equal to the rate of flow of charge, or the charge divided by time. And the second equation is the one that we introduced at the beginning of this lesson. So the voltage, or the potential difference across a device in a circuit, is equal to the energy transferred to this device divided by a unit of charge. And with our power equation, we need to replace the right-hand side of it with some combination of voltage and current. So how can we do this? We could rearrange equation 2 here and isolate the work variable. We can now replace the work done in our power equation with the voltage multiplied by the charge. Notice though that our current equation looks identical to the fraction in our power equation. So now we can replace Q divided by T with the symbol for current, and we end up with this equation. So this equation can be used to calculate the power in a device when we use a voltmeter to measure the potential difference across this device, and an ammeter to measure the current flowing through it. So with this information, we can answer this question. An electric kettle has a power of 2.2 kilowatts at 240 volts. Calculate the current flowing through the kettle. We need to rearrange this to make the current the subject of the equation. All we need to do is plug in the values that we got in this question, and we get a value of 9.2 amps to two significant figures.